nobody came out and ran with us this morning. It was just me, Benita, and somebody else. Remember that we do have our monthly faculty runs on 9, 10, first Wednesday of every month, currently.
I'm training for a marathon, but I can't.
It's only 5K, so it shouldn't impact your training regimen. I was not probably going to do it until this morning. It got up to 17 degrees, so that's good enough. And there's no wind chill, so it was good enough. Right. Anyway, next one will be March 1st, 9 a.m. Right. Meet outside of shore. All right, so to go back to Python though. Python, you can create classes, and we did this with a student class here. Very quickly we put this together. We realized, however, that there's no strong encapsulation. In other words, there's no protection of this data. Once you've created a student, you can go ahead and add whatever properties you want to it. You can get those properties, you can modify those properties, you can do whatever, right? So for example, I just added this age here. There's nothing to stop me from going, say, Bob's age there, c.age. We'll go ahead and put him as -10, right? There's nothing to stop me from doing that, and there's no way to validate that stuff because there's no strong encapsulation. But in any case, once we've got a class, that begs the question of, we need to sort that stuff. We need to search for a particular student. We'll want some sort of a way to process this data because we've got a class, a way of representing that class. 2 detours before we do that. The first detour is, if you do not want a full class, a tuple may be a good solution. So for example, this is a student, and the student is a number that represents an NUID, another number that represents an age, and then 2 strings. Right? There's nothing to stop me from saying that A is those things, right? Now that's a tuple. That's a group of 4 things. If it were only one thing, right, there, or 3, there we go. That's a tuple of one thing, a singleton, we call those. If you have 2 things, what do we call that? We don't say a doublet, do we? A doublet would be, what is a doublet on a jacket of some sort, isn't it? All right, nobody knows 17th century fashion, neither do I. We call this thing what? A pair, right? If there were 3 things, what would we call that? A triple, right? Quadruple, right? Anyway, we call these things tuples in general, right? And if you don't want to go to the effort of creating an entire class and you just want to group things, you can do it. Why is that nice? And because what you can do is you can write a function that can now return 2 things, right? So for example, let me write a function here, add 1, or I don't know, a pairing. What would be a pair, right? Def, I don't know, I'll just make it up here. We'll take a number here, and then we'll return x plus 1 and x minus 1. There we go. So if I gave you 10, this would return a pair that consists of 11 and 9. Right? Let's go ahead and call this function. Let's say b is equal to foo of 10. And let's go ahead and print a, and then print b. Let's see if this works. I think I'm going to have to do something extra here, but Python demo. Yep. Oh, no, it worked. Right. So do you see what I did there? I create a function that can actually return a tuple, which is technically just one thing. It's a grouping of more than one thing. So it's returning a pair. And then what I can do is I can not dereference, but I can put those pairs into actual variables here, a and b. Right? You can use this trick to do things like, for example, if you've got x is equal to 10 and y is equal to 20, what you can do is you can go that x comma y is equal to y comma x. What am I doing there? Swapping them. Swapping in one line, one-liner. Right? And it's because of these kind of groupings and these tuples and stuff like that, right? So you can do little tricks like that, right? So here's, that's our detour. Detour 1. You can return tuples from functions to return multiple values, right? You can assign values using tuples. Or you can you do things like this and remove the tuple entirely and simply just use something to swap it with a one-liner. Right? Okay. Our second detour here would be how to sort normally, ... Right? What I mean by that is, let me go ahead and create an array here, or not an array, but a list. Numbers is equal to 5, 8, 4, 6, 2, 0, 1. There we go. Okay. Now I want to sort those numbers. Right? Let's print it out first of all. Print numbers. Because we're going to print it out once we've sorted it as well to verify that it's actually sorted. So this is unsorted. How should I sort the numbers? One way of doing that is numbers dot sort. Right? And let's go ahead and print it out again to see if that worked. 0, 1, 2, 4, 5, 6, and 8. Great. That works for numbers. What if you wanted to sort it in reverse order? Numbers dot sort reversed is equal to true. Right? All I need to do is provide an argument there, and this is a parameter, but I'm naming that parameter and I'm setting it to be true. The default is going to be false. And this should work, I think. Let's find out. Should then be 8654210. Right? All right. It works for numbers. It works for strings. Well, let's test it for strings. Right? So let's go ahead and go with names is equal to me, Bob, Alice, and Zoe. There we go. And let's go ahead and sort that. Names.sort. Right? And print it out. I won't bother printing it out beforehand. There we go. So Alice, Bob, Chris, Zoe. What if I had done lowercase Zoe? What order is it going to be now? Who's going to come first now? Oh, wait. Sorry. Lowercase a Alice, right? Yeah, because caps come before lowercase in the ASCII text table. And now who comes first? Come on. Bob should come first. The same order as before, but where's Alice going to be now? At the end. So what does that tell you? It's lexicographic, right? How do we go about doing it? Ignore case. There's a way of doing it. I forget off the top of my head. Right? There's a way of doing it using a key that we'll talk about here in a moment. Right? What else? You could reverse that. Okay. Sorted copies. Right? Instead of using .sort, use sorted. Right? So sort is, now we're getting into grammar, right? What kind of verb is sort? It's a transitive verb, right? Sort that thing right there. That's the direct object. But sorted, what kind of verb is that? Isn't it present perfect, or it's past perfect? Like it's a state of being. It is sorted. So what we're going to have here is a copy. Let me go ahead and redo this. So there's Alice at the front again. And then copy, sorted copy, is going to be names.sorted. I think this is the way you do it. Let's find out. Print sorted copy. There we go. Oh, nope, not names.sorted. It's sorted, and then you pass it in names. There we go. That's the difference. There we go. Alice, Bob, Chris, and Zoe. And that is a completely new copy here, because if I were to print the old copy, print names, you'll see that it retains the original ordering there. Chris, Bob, Alice, and Zoe. But then the copy is Alice, Bob, Chris, and Zoe. Right? So sorted copies, instead of using sort, you use sorted. And then you pass it in as an argument. Right? Up here, I've got 3 students, Alice, Bob, and myself. Right? how do we go about sorting those? Let's try it first. So roster is equal to A, B, and C. Did I call, I think I reassigned them, so let me go ahead and recreate them down here just to make sure that A, B, and C are those 3 students. Okay. There's my roster. Let's go ahead and go with roster.sorted, or sort, right? And let's print it out. Print roster. Actually, let me try something. Let's print it out beforehand to make sure that it's actually Chris, Alice, and Bob, right? And then we'll try to sort it, and then we'll try to print it out again. The first thing I want you to notice here is, did that print statement work? Student object at a memory address. Student object at a memory address. Student object at a memory address. It didn't work, right? Why? I did the string overload here, right? It didn't work because that's not the default. You need to bring in that pretty printing library that we talked about before. So import pprint, right? And then you can go ahead and pretty print it. pprint.pprint roster, and print it out again out down here. Okay. Now, let me actually print a bunch of spaces or empty spaces so that we don't confuse the output here. There it is. It's it should be pretty printing the darn it. It should be pretty printing this stuff now, right? Get how to do it then. What we can do is we can go with representations that repra. There we go. I think that will work. There we go. You don't want to do that generally though. So there's me, there's Alice, and there's Bob, right? Bob Burke instead. So under the hood, there are 2 ways of creating a string representation of a Python object. One of them is str, right? And this would work perfectly if instead of using pretty print, if I printed out the roster manually. So for student in roster, right? Pprint that student s. This will work fine using the string. It should be come on. Oh, that's right. str. There we go. str. So I have to force it to call the toString method there. Okay. And there's me, there's Alice, and there's Bob, right? However, I'm just forcing it to become a string representation. What I did before was REPR, repr. That's short for representation. If you need to take a Python object and then serialize it to a data format that then can be saved to a file and then opened up again in another version of Python, you would generally use REPR. This is also built into Java, by the way. It's called serialize. It's not something that you ever really do manually anyway. You bring in a library to do it. But that's another way of doing it. And we're going to stick with str here. It's just that the problem is you need to force it into a string representation. Right? Another way of doing this would be roster as strings, right? Using a list comprehension. I just found out this morning that the Python folks in the other section were never exposed to comprehensions at all, right? And I was absolutely floored because that's the way that you do things in Python, right? I want a string representation of s for s in roster. And now I can go ahead and just print out that roster as strings. I don't even need the pre-printing library, roster as strings. There we go. And there we go. Burke, Alice, and Bob. Now, come to line 70 here. Is that sorting call working? Nope. What's it complaining about? I don't know how to compare those things. I've got this student and this student. I'm trying to say this thing is if this thing is less than this thing, then it's in order, right? Or it's out of order. In C and Java, we solve those problems by creating comparator functions or comparators. The way that you do it in Python is by providing a key, right? And I'm not sure on the syntax, so I'm going to have to refer to my notes here. Bear with me. I think it's key is equal to lambda. This is a lambda function. Yep. Key is equal to I should have trusted myself. Lambda, right? So does anybody know what a lambda function is? A lambda function is nothing more than a fancy term for a function without a name, an anonymous function. Up here, when I created this function, where was it, foo? I gave it a name, right? Its name is foo. If you create another function, square root, it has a name, square root. A lambda function is just a function that exists in line without a name. It's anonymous, right? It's a way of writing a function without having to actually write a function, right? So lambda, what the syntax here is going to be x, and then x is, say, or dot, let's go with age. There we go. Right, there we go. So what am I doing there? I'm saying, I want you to sort this roster. How am I going to sort it? By keys, right? That this key comes before that key. And then I'm saying that, well, what should you use as a key? You should use x's, it should be x dot age, right? X dot age. Oh, no, x dot age. There we go. You should use x's age as it, right? So here's an element x. Here's another element y, but we don't have the variable y in this context. We just have x. Well, what should you use to compare x to other values? You should use its age, right? This would be like, say, instead would be like a getter, right? So def get age, right? Return self.age. And then I would use this function here as my key variable, or as my key to sort stuff. But instead, what I'm doing is I'm saying, don't bother with that. Just create this anonymous function. It has no name. It's not get age. It's not get the age of the student or anything like that. There's no name. It's lambda, right? Lambda is the Greek letter, Greek letter that in the context of computer science means nothing, right? So the lambda function. The lambda string is the empty string in theoretical computer science. Yeah.
So if you want to sort it by age from descending order, would you just do dot sort dot reverse, or is there like a better
Comma,
way to do
reversed,
that? Okay.
reverse equals true.
Okay.
Yep. So this is an argument. Set the key to be whatever this thing is right here. Set the reverse to be true. Right? So let's go ahead and go with, what did I do, age? So now it's going to be oldest to youngest. Let's see if that works. There we go. Here it is. Bob, Chris, and Alice. And we're going to have to look up there. Bob is the oldest. He's 54 years old. I am only 21 years old, honest. And then Alice is 16 years old, and she's last. Right? And if we did not have that reverse there, or if we set it to false, which is the default, then we would get just Alice, then me, then Bob. Right? So how would you do other things, like, say, last name? Right? You want to go last name, and then not in reverse. It would be Burke, and then Zeno. Right? Burke, Zeno. Is that right? Chris, and then Bob? Nope. So how do we go about doing that? It's not so simple in a lambda function. Right? If you've only got one key, a lambda function is what you want to use. If you want to have more complex stuff, for example, I want to sort by last name, but then if they've got the same last name, then break ties with the first name. If they've got the same first name, we've got 2 John Smiths in this course, then we need to go to the NUID. If you need to do that complex of a chain of comparisons, then you should be using what's called a decorator pattern, Python comparable object. What is it called? Darn it, I forget off the top. Comparable classes, there we go. You want the total ordering. Func tools total ordering, right? Let's go ahead and open that link and check and see what it looks like here, right? So what you need to do is you need to use this annotation here. A total ordering is an ordering of things where everything is comparable, right? If I just looked at John Smith and John Smith, those two things are not comparable because there's no way to break a tie, right? They're for all intents and purposes, they're the same thing. They're the same person. But if you need to go and break ties to make it totally ordered so that John Smith with NUID 1, 2, 3, 4 is different than John Smith with NUID 5, 6, 7, 8, right? then you need a total ordering. With a total ordering, and that, by the way, you have to bring in, where is it? Func tools. You have to bring in, well, here, I think we could do it really quick if we wanted to. Import func tools. There we go. What do you think func is short for? Function tools, right? And let's see, total ordering. There we go. So let's go ahead and make our class a total ordering. And let's go ahead and put that up here. Right, there we go. And now to make something a total ordering, there are these magic functions: equal, EQ, LT, less than, greater than. There's also less than, equal to, and greater than or equal to. But if you read the documentation here, here they all are. Less than, equal to, greater than, equal to, or equals. Basically, you only need to do at least 2 of those. All right? Once you do 2 of them, then it can call the appropriate one to make the comparison. So for example, let's come over here, EQ, def EQ, underscore EQ, underscore self, and we don't take anything else in, do we? Yeah. Oh, and other, the other one, right? There we go. Other, right? So if they're equal, if what? What's our logic going to be here? If they have the same first name, same last name, and then the NUID is the last thing that we compare. So, darn it, return. Yeah, I'm just going to take this. I'm going to steal this code right here. Self dot last name, and this one is case insensitive because it does lowercase. I don't want case insensitive. We'll go last name. There we go, and not lower. And then first I do need first name here. First name and then last name and then self dot NUID. There we go. And then other on all of those other ones. Other. There we go. And this will be other, but I've got to spell first, right? First, other, and other. All right. Really nice syntax there, right? This thing is equal to this thing if their last names are the same, and their first names are the same, and their NUIDs are the same. What am I using here? A tuple, right? Really powerful stuff. Triples, doubles, right? I can just say that if all 3 of these things in that exact order are equal to all 3 of these things in that exact order, right? And I don't have to say and then do dot equals, or whatever. Right? That's EQ. What does less than look like? I'm going to steal this as well. Right? I'm going to get myself in trouble by cutting and pasting a lot of stuff, I think. There we go. So, what is that syntax? Same exact as before, but what do I do now instead of equals? Less than. Right? So compare their last name, and it's ordered. Tuples are ordered. There's the first element, the second element, the third element. So last name, then first name. If those 2 things are the same thing, then it goes to the NUID. Right? And now let's see if this works down here with just sorting them. Let me go ahead and get rid of all of this, except for that. There we go. Roster.sort. Right? That encapsulates all that logic in the class itself. And I don't have to worry about Lambda functions. I don't have to worry about pulling stuff out and comparing stuff, whatever. That should work. Is not defined. Fine. Right, total ordering. Yes, it is. It's in the func tools library, isn't it? Oh, maybe from func tools. Cross my fingers on this. Import from func tools. Import total ordering. Crossing my fingers in this. There we go. That's how you do it. Don't bring in the entire func tools library. Bring in just that thing that you want, that total ordering annotation. Right? And so Python is smart enough to see that you intend for this class to be a total ordering, and so it's going to look for these magic functions in there when you call the plain old sort algorithm. Right? And is it correct? Burke, comma, Bob, then Burke, comma, Chris. Yes. Right? And if we had two Bob Burkes in there, let's go with D is equal to another Bob Burke, but with a different NUID. 1. There we go. Same age, same name, but for some reason they have a different NUID. We'll add them to the roster. We'll sort it. Come on. There we go. Bob Burke with 1 comes before Bob Burke with 4213. Right? So in Java, how would you do this? You would make a class comparable, or you would create a comparator. In C, how would you do this? You would create a comparator function. Right? In Python, there are several different ways of doing it. You can do it with a lambda function if it's simple enough. If it's more complex and you need to break ties, then you probably want to bring in the functool library. Right. All right. Any questions? No? Okay. Here's the full demo, Python. There we go. All right. One question would be, what about binary search? So let me get rid of all this and go numbers is equal to just random numbers here. Well, I can't randomly mash the keyboard and have it work. There we go. All right. So now can I do a binary search on something that's not sorted? Nope. So numbers dot sort. Okay. Now, how do I do a binary search? Let's print it out. Print numbers. Right. And come on. There we go. There it is. It's sorted. Now we can do a binary search. Right. Binary search in Python. Nope. There is no built-in binary search algorithm. There is no built-in binary search function. You can search for binary search implementation in Python and then steal their code and use it if you want to, but that's not the Pythonic way, right? The Pythonic way is to use dictionaries instead. The Pythonic way of doing stuff is to use dictionaries, right? Dictionaries have fast order one, constant time algorithm, lookup using the keys, right? So no, that's not built in. I can't show it to you because it doesn't exist, right? There might be some binary search buried in some library or something like that, but I don't think it's standard. In fact, why does Python not have a binary search standard function? It has dot sort, right? Bisection, yeah. How to do a binary search in Python, that's just, they're just going to give you implementations for it. And again, the reason is, why would you want to binary search anything, right? You've got these things called dictionaries. You can look up stuff, you can look up stuff so much easier using a dictionary, right? So for example, how would you use a dictionary to solve the third problem in your assignment, where you've got a bunch of weather data with timestamps and temperatures, right? Think about that, right? Dictionary is what you're going to want to use, okay? So no binary search, sorry. Right. If you want to, you can bring in a binary search if you want to, but that's not really how it's done, okay? All right, we've got 20 minutes left. Here's homework 1 from last year. Right. It was in PHP, right, and it was in Java. Very, very similar to what we've done. The format is very similar to what we have right now, where you're given these 3 simple programs, and guess what? I had used those programs in fall of 21, right? Just like the programs that you're assigned in assignment 1 were used in fall of 22. Right? All right, so the first one is a Pythagorean expectation. So everybody knows what the Pythagorean theorem is, right? The sum of the squares of the 2 sides of a right triangle is equal to the square of the third side, right? Just like the scarecrow screws up, right? We all know that, right? From Wizard of Oz. He tries to recite the Pythagorean theorem, and then he gets it wrong because he says obtuse or acute or something like that instead of a right triangle, right? All right, well, it turns out that the Pythagorean theorem can actually be used to predict how well a sports team will do. What you can do is you can take their win-loss ratio of the entire season and predict it pretty accurately if you have a sample of what they've done up to this point. So even like 10 or 15 games into a season, this works for any sport, by the way. 10 or 15 games into a season, given the number of points that have been scored against them, given the number of points that they've scored, what you can do is you can put this into an expected win percentage, a Pythagorean theorem here, because it's you square this, right? You square it, and then you square this one, and you square this one, and you divide it by it, and you get some numbers here. Right? I've got it set up for baseball here, where there are 162 games in the season, and then these are runs scored and then runs against. Right? It turns out to be super, super predictive. Right? Even with a small amount of data, the number of predicted wins here, 67 wins. The performance was only 4 wins off, right? And this, it turns out that this is extremely powerful. Why? Because a good team doesn't suddenly become bad. A bad team doesn't suddenly become good. And a middling team is going to stay a middling team, right? You might have ups and downs, but if you just take a representative sample, you can pretty much predict what they're going to do, right? So what's the point of watching a 161 game season when it's kind of almost already decided a month into the season, right? That's sports. Anyway, we could do that with a bunch of different p-values here, and then come up with a predicted win percentage given the runs against, the runs scored, and then 162 here is hard-coded because it's for baseball. Then we would round. Another exercise here is entropy, which is much simpler. That's what we're probably going to start with here. Entropy is a measure of information in a piece of data. So for example, if something were completely random, right, random background radiation or something like that, there's no rhyme or reason to it. It has very low entropy or high entropy. Higher entropy value corresponds to more random data. I think that if you normalize it, the highest entropy rate you can get is 1. Completely 100% random. But other stuff is highly ordered. For example, if you take plain old English, right? Like if you measure the entropy of an English language page of actual text, it's going to have low entropy. In other words, it's going to have high information. With random values, there's no information at all. But with structured language, there's going to be a lot of information in there, right? One way of measuring that is through Shannon's entropy function, okay? So what this is each x of I here is a character in a string, right? So uppercase A, lowercase b, space characters are used as well, and even commas, and anything in the ASCII text table, right? So each one of these is a character. P is the probability of that character. So for example, if we have hello world here, right, there are 8 distinct symbols. O, lowercase o, is repeated twice. Lowercase l is repeated 3 times. So the probability of L would be 2727, right? Why? Because 27% of all the letters in this string are lowercase l's. 18% are lowercase o's. And the remaining are all equal because they're all unique characters, and they're going to be 0.0909. If you plug these probabilities into this equation up here, and then you take the log base 2 of those probabilities, you sum them all up, and then you have a negation out front, that gives you a measure of Shannon's entropy function here. Okay? So the entropy function for hello world would be 2.845351. We can do it for a simple string. We could do it for a full file, right? Let's start out with that. Let's start out by trying to measure the entropy of hello world. Now, why is this a good measure of information, right? Think about English. What is the most common letter? What's the most common vowel, I should say? E, right? Then A. What's the least common letter? I think Q, right? Z is a little bit more common, but they're about the same, right? That tells you that the distribution of letters in a natural language is not uniform. It's not random, right? It makes sense because there's information in language. This is a way of measuring that information. Right? Let's come over here and start afresh here. And let's go ahead and solve this problem. Let me go ahead and start out with a test string here. Is equal to hello world. Our expectation for this entropy was going to be what? Expected entropy is equal to, and I'm going to steal this. There we go. All right, there. Let's write a function to do it, first of all, right? Def entropy, right? Remind me, how do I write this function? What am I going to take as a argument here? The string. Let's just call it S. All right? So now let's outline this function. What are you going to have to do first of all? 1. I'm going to have to go through and count all the L's. I'm going to have to go through and count all the O's. I'm going to have to determine the length of the actual string, right, so that I can compute all the probabilities. For example, for L, for lowercase l, it's going to be, there are 3 of them in there. How big is this string? 5, 6, 7, 8, 9, 10, 11, right? That's going to be 3 divided by 11, which is equal to, according to the handout, it's 2727, right? I need to do that for each letter, right? So let's go ahead and outline this, right? For each letter in the string, dot, 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 2, or subtask here, count up the number of times, or times it appears, dot, 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 right? Then, 2, compute the probabilities of each letter, right? 3, sum up the probabilities times log base 2 of the probabilities, right? And then 4, return the result, okay? So I could go through and capital H and go through the rest of the string. How many more times does capital H appear? I could do that for lowercase e. How many times does it appear? Just once. When I get to that first L, though, and I go through and count up the number of times an L appears, 1, 2, 3, what happens the second time that I get to another L? I'm going to go through and count up the number of times that L appears again, which is now 2. But I already did that once. Right? So this is the idea, but you don't have to do it that way. Any suggestions? What about if I went for each letter in the string? Right? Increment a counter for that letter. Right? Do this using a smart data structure. Smart data structures in dumb code are a lot better than the other way around. What smart data structures have we seen built into Python already? Lists, sets, and dictionaries. What if I used a dictionary? What would I map? Map a letter, say L, to the number of times it appears. Right? So that this is the first time I've seen L. How many times have I seen it? 0 so far. This is the first time. Increment that counter. The second time that I see an L, how many times did I see it so far? 1. Increment that counter. The third time that I see it, how many times have I seen it so far? 2. Increment that counter. Now it's 3. Okay? So for each letter, that's the idea. Let's actually write code to do it. Right? And then come back and erase this, because that's cruft. That's just me outlining stuff. Right? So for each letter in the string, for each character in S. Right? Let's make sure that this works. Print C. There we go. And down here, let's go ahead and go actual entropy, or computed entropy, is equal to entropy of what did I call my test string? str, right? And then let's output that. Print formatted actual value is equal to computed entropy, and then expected is going to be, what was it? Expected entropy. There we go. Right. And you see how you can start doing, you know, ad hoc unit testing like this, right? Just like we did in C. But why use a formal unit testing framework like unit test instead? Let's go ahead and run this to see if it works though. Right. There we go. Hello world. Right. So it is actually incrementing over each character. That works. So for each letter in the string, increment a counter for that letter. Instead of printing it out, let's go ahead and get the number of times that we've seen it so far. Count is equal to, here's where I need my dictionary. Right. So here's a dictionary. Right. So character, or char count, right, is equal to a new dictionary. Now you could go through the entire ASCII table and put in zeros for everything, initialize this. Well, I haven't seen any lowercase a's yet, so I'll go ahead and map that to 0. I haven't seen any lowercase y's yet, so I'll map that to 0. Why? Right? Don't bother. Right? What we're going to do is we're going to ask whether or not that character is even in the map itself. Right? If C in char count, right? There we go. Then what we'll do is we'll say that the count is equal to char count. And now how do we get something out of a dictionary? We use that square bracket notation. Here's my key, C, right? There's the count, right? Increment the count because now you need to add one to it. And then put it back into the map, right? So char count of C is equal to count. I could, oh, good. It's italicizing this, and it's trying to give me a hint. Can you do that in Python? Nope. Plus equals 1. That's how you have to do it, right? So again, the idea here is if this key is in this map, is in this dictionary, then that means that you've seen the letter before. Get how many times you've seen it before, increment it by 1, and then put it back in the map for next time. Otherwise, this is the first time you've seen it. What should you do? Char count of C is equal to, if it's the first time you've seen it, it's 1. Now, at the end of that for loop, let's go ahead and p-print this out, print.pprint char count, just to make sure that it works. I'm just doing ad hoc testing here. Right? And I don't have pprint in here, so import pprint. Okay? No, I did not mean print. I meant, okay, so it didn't save. There we go. The space, how many times does it appear in the string? 1. Capital H, how many times does it appear? 1. 1, 1, 1, 1, 1. Capital L, or lowercase l, how many times did it appear? 3. And O is 2. Awesome. All right? Okay. I am pretty sure that it works up to this point. Now what do we need to do? We need to compute the probabilities of each letter. So probs, right, is equal to a list of those things, right? And what I can do is for key value in my map, key value in char count.items, right? That will give me the character, and I shouldn't call this key K and V, I should call this the character, and I should call this the count, right? And that will mean that I'm putting in, say, oops, there we go, probs.append. What's the probability that char is in there? It's the count divided by the length of the string, which is just len of s. There we go. Let's print that out. pprint.pprint. And that's going to be probs. That is not the Pythonic way of doing things, but it works. 0.27, right? What's the more Pythonic way of doing this? Why do, yeah, a function, or what are you thinking of making? Oh, I need to make a new list, right? So instead of doing something like this, it's just going to be count divided by length of s for count in char count. I think that that's for values. What did we call this? Do you remember? Where you create a list out of another list. We're using a for loop inside of it. Do we understand it? If we understand this, then we comprehend it. Right? This is a list comprehension. I don't know that this will work. I think I need values. Yeah. Dot values. There we go. There. There. And let's print. Oh, I took out my pprint. Pprint dot pprint probs. Now remember, those probabilities are 0.27, 0.18, 0.09, etc. Right? A one-liner. That's the Pythonic way, right? Everybody's heard the expression, when in Rome, do as the Romans do. When in Python, do as the Pythoners do, right? So sum up the probabilities, right? So for this one, I don't know off the top of my head. So let's just go ahead and go with a sum. Actually total is equal to 0.0. And then for p in probs, the probabilities, what I'm going to do is total plus equals prob, or p, times log base 2 of p. Except I don't think that that's an actual function. Does the math library have a base 2 function? Let's find out. How do we find that stuff out? Python, log base 2, I don't want numpy. NUMPY is the answer to like a million different questions online. Log base 2, import math. Okay, oh, yeah, excellent. There's a 2 argument there. Hopefully this is an accepted answer. Let's find out. There we go. Math p base 2. Anybody can confirm that? Of course, I'm going to have to bring in import math. Right, there we go. There's the sum. There's the total, and then I return the total. There we go. So the expected actual value, expected value. Oh, and then what did I forget to do? What's out front in that summation? Negation. And once I do that, then perfect. All right. Now, 2 minutes left. We won't do it, but 2 minutes left. You would have to change this for the actual assignment and accept stuff as command line arguments. In fact, you'd have to do an entire file, right? Here's a plain old English text file, right? What is the entropy of that entire essay, right? And you could do that very easily. How? 3 lines of code to pull in file open, read lines, concatenate all that into one big giant string, pass it off to your function, close the file, right? And then pass that off to your function and you're done. If we want to see that next time, we can. Otherwise, we'll do one of these other exercises from last year. Any questions? So now are we liking Python more or even less now? More? Okay, all right. All right then, have a good time in your lab, I guess.